We're right on 4 o'clock, so we might as well get started. Like a good stream on time. So we're very fortunate today to have with us lecture. This is Karen Flack from the U.S. Naval Academy. She earned her PhD in 1993 at Stanford. From there, she went directly to the Naval Academy, where she's been on the faculty mechanical engineering since. Her expertise is in well-grounded turbulent flows. She's a fellow of the American Physical Society and has received the Pike House and Teaching Award, the U.S. Naval Academy Research Award, the United States Government Meritorious Service Medal. She was I invited her. One of the reasons I invited her is that perhaps the number one thing that makes architecture really very interesting is the fluid structured interface. That's the one thing.
That's it. The only.
The transmission of steady and unsteady forces across this interface, of course, there buoyancy, drag, wave loading, structural excitations, hydroacoustics, etc. Sets the design parameters for powering, sets the shape of the ship for sea keeping. Okay, so Professor Flack is part of the Navy's top resource for the shear stress and drag is associated with structured interface. And this impacts almost all of it. So it's not like this is a fringe topic. This is the topic. So with that, thanks for coming. And we look forward to what you've got to say.
Thank you. Thank you, Professor Dowling. Ah, very nice. Thank you. Thank you. Thank you for inviting me and that setup. I'm a little intimidated, but I'll try to live up to that introduction. I've really enjoyed coming to Michigan. This is my first trip to the University of Michigan. I'm very excited about getting out and seeing your campus. I'm very excited about seeing Ann Arbor. And I enjoyed seeing the design presentations I've already seen this morning. Thank you so much. I'm impressed. I have more hard questions for you during the reception, okay? All right, so as said, I have been working on wall-bounded flows and with these amazing colleagues, Mike Schultz, Ralph Volino at the Naval Academy, and my international colleagues, Daniel Chung, Nick Hutchins at the University of Melbourne, and Giulio Barros in Japan. I'm going to present some work that I've done over a lot of years. I've been involved in all of this work, and I've just had some amazing collaborators through the Navy. So here to motivate this will motivate the Naval Architecture Program. So we know roughness is a penalty. Okay, when you have biofouling on your ship, you clean it. You don't say, yay, I've got more biofouling on my ship. This is really going to help out, right? It's a penalty to you. It's a penalty in fuel costs. It's a penalty in performance costs. And so it's important that we understand what that penalty is and what it'll do to your powering penalties and basically your performance penalties. And so my colleague Mike Schultz published his paper back in 2007 in Biofouling. And this is the increase in ship shaft power, % increase, if you have these surface coatings, okay? Hydraulically smooth, that's not what it is, okay? It has an anti-fouling coating painted on it, paint. The paint causes a 2% increase over hydraulically smooth. However, if you have a very deteriorated coating or light slime, look at that number. It's already in the 10% range. This is a light slime film of biofilm. Okay, that's already a huge cost of fuel. Okay, you get into heavy slimes. Down here is when you start to think, oh, well, you know, someone really needs to clean that. There's calcareous fouling, weeds. You can get up to barnacle growth. Okay, so you can show the penalty is significant. Okay, so it's important for the kind of ship husbandry, cleaning the ship holes and the kind of the cycle of that you understand what your penalty is, your fuel costs. And now when we're talking fuel, we're talking carbon emissions too. So there really could be a lot of carbon savings by understanding when to clean your ships, okay? But that's kind of the simple answer to this. Now I'm going to get into the complications, how we know and how we predict the drag on ships, okay? All right, we've seen this before, right? The very famous Moody diagram. I love this diagram. The reasons I love it is it's Non-dimensional versus non-dimensional. That makes me very happy as an engineer. It also has a lot of information packed in this. I remember as an undergraduate looking at this diagram and being fascinated by the fact that this Reynolds number, you know, it didn't matter if it was water or air or oil, it was all packed in there. Okay, so we've got this Reynolds number versus friction factor, which is basically some sort of non-dimensional drag coefficient. And for over here, we have this non-dimensional roughness height, where this is for pipe flow, right? So we go with this idea where the flow is laminar, then it goes to turbulent at higher Reynolds numbers. This lower one is for a smooth pipe. And as you get higher and higher values of roughness height to diameter, you know, your drag increases. There's a point in this curve where it's curved, which is called the transitionally rough region. Then at some point, the line goes basically flat. And that's the fully turbulent zone, or the fully turbulent flow, or they call it the wholly turbulent flow. Okay, well, what's interesting over here is this roughness height. You think, okay, well, that's just the height of whatever the roughness is. How do you categorize that? Is all roughness the same height? Does biofouling have one uniform height? Does corrosion have one uniform height? No, you don't. So basically, we come up with something called the equivalent sand grain roughness. It is the same height of Nicarazzi sand or sand grain that would cause the same drag in the fully rough regime over in this flat section, this independent of Reynolds number regime. It is not a physical measure of the roughness. If you remember one thing from this talk, the equivalent sand grain roughness height is not a physical measure of the roughness height. It is a hydraulic scale. You have to run a test, or you have to do a very complex computational simulation in order to know it. And if you don't know it, you don't know it. Okay, so really, this whole talk is about what is KS for a given roughness. Okay. So if you have a ship hull, you would like to get that KS, equivalent sand grain roughness height. And it's a function of the average hull roughness, basically. They go in, and they take profilometer measurements. A profilometer is just a fancy term for something that takes a surface profile. Over 50 millimeters, they figure out what the RT50 is, which is the peak to trough roughness height over a 50 millimeter range. They take a bunch of measurements and then they average it, and they get that, and they say the KS effective is some function of that. What is that function? Okay, it's going to be a function of that, but what is that function? All right, and that's particularly important because look what your ship hull could look like. I don't know, maybe at the bow it looks like that. Maybe at the midship it's got this kind of tube wormy growth going on here. And maybe again you got some kind of barnacle stuff going on in the stern. Okay, and it's not going to look like it the entire, you know, whole section. And this is kind of some pictures, obviously, from the USS Gary, FFG 51. Okay, it's not the same ship. That's Scranton, that's Hamilton. All right, so it's not from the same ship. But the idea is notional, that you can go down and see what this looks like. And obviously, this is going to have some equivalent sand grain roughness height for this one, and this one, and this one, and this one's kind of dense, and this one's sparse, and you know, it's a mess. Okay, and this is why it hasn't been figured out yet, because they would have figured it out long ago, but they haven't. All right, so here is kind of the goal. Predicting drag on ship hulls. First of all, we need to develop a robust model that determines the dependence of the roughness hydraulic length scale as a function of the surface topography. KS is a function of your profilometer measurement, or some measure of something that you can go down and easily measure. Okay? We really would like this to be a low order model. It can't be that complicated. You just have to be able to know just by some easy measure. You need to incorporate non-homogeneous surface texture, meaning multi-scale, patchy, and have it be applicable to Naval, for the Navy, who I've worked with, and other platforms, the commercial shipping industry. All right, so here's where we're going to get into theory and why we can do this. How do we model roughness and predict drag? This is basically a turbulent boundary layer non-dimensionalized with the free stream velocity and distance from the wall. Okay, you have this kind of sublayer, then you have this log law region. And it's very important when you have rough wall boundary layers compared to smooth wall boundary layers. It turns out this is a beautiful, beautiful result that you get this kind of parallel log region. It just shifts downward. It looks the same. It's similar. Similarity is a huge term in fluid dynamics. It's similar. It looks the same. And so what we call this shift in the log law is this roughness function, or basically the momentum deficit that is caused by having the flow go over roughness. And so you can kind of put that into your log law as just this kind of shift, this roughness function. Okay, so let's say you go in and somehow you measure this roughness function as a measure of the roughness height. And you've done this by taking a whole lot of boundary layer measurements or somehow getting a friction curve or something so you can get what this roughness function is. And now what we're going to do is we're going to plot the roughness function as a function of roughness Reynolds number. And I've defined that as my length scale in the Reynolds number to be the characteristic roughness height. So this is what this curve might look like for, I don't know, a painted surface, a scratched surface, a sand grain surface. This is all kind of cartoony, notional. And if you have that, then for that surface, now I know what the roughness function is as a function of K plus. What I can do with that is I can now put that into wall functions for computations, which then goes into my lower order RANS models, which are pretty great, or large eddy simulations, wall modeled large eddy simulations. This is the parameter. If you know delta U plus, you can then do these simulations. However, you had to have run this for every single surface. If instead you go back to our friend, the equivalent sand grain roughness height, and you use the equivalent sand grain roughness height in your roughness Reynolds number, you come up with this equation and they all collapse in the fully rough regime, basically where the friction factor was independent of Reynolds number. Remember the Moody diagram that went straight across? That's the regime. So this is valid every time you're fully rough. It is not valid in this transitionally rough regime. Okay? And so if you can figure out this roughness function as a function of the equivalent sand grain roughness height, it's valid for any roughness in a fully rough regime. Again, you need to know KS. That's what this talk all comes down to. You can also take this from lab scale results to full scale, and you can create these Moody type diagrams. And this is some wonderful, wonderful results, similarity scaling of Granville, who worked for the Navy, who came out with this beautiful idea where you can take the friction coefficient, the overall friction coefficient as a function of Reynolds number based on length of a plate. You have your smooth line, you shift it by the roughness function, and then you go from your lab scale on this line of constant to ship scale. It allows you to do lab scale to ship scale modeling, which is very important. Okay, you can also create a Moody type diagram, which I did here because it's very pleasing again. It's really what's going on here is that's just an equation, but I put it here in the Moody diagram, which shows basically your overall friction coefficient as a function of log of the Reynolds number based on length. And there is your equation for what it would be for a plate of length L covered with something of KS of a given sand grain roughness height. This would be what your overall friction coefficient would be. Just says basically, this is a scaling as it goes. Your roughness function goes as some log of the equivalent sand grain roughness height Reynolds number, which brings you over here that your change in friction coefficient goes as the log of KS plus quantity squared. Okay? Again, what we really need is KS. And it would be beautiful if we get it as just a function of the surface topography. And you don't have to run your hydrodynamic test. You just get some kind of profilometer measurement. Okay, so we go back to this. Okay, this is work that's currently being done by Mike Schultz and Nick Hutchins, and this is very, very clever. Okay, I didn't have anything to do with this. This is the only part that I didn't. I'm gonna show you what they've done. Oops, I'm giving you the preview before I pack it up. All right. So we're gonna come up with an effective way of including all of these kind of, range of surfaces as you move from, from bow to stern, incorporating these ideas of having different regions. Okay, they said, what happens notionally if you have, span-wise roughness heterogeneity? So 10 scales, this looks like that. Okay, it's not going to look exactly like that, but this is the idea. They found that you can do your best estimate of this by using this, instead of just an average, a power mean. Okay, what that P is, they know, but they're about to publish it, so I'm not going to tell you what P is yet. Okay, you're going to have to read the paper. Okay. If you go streamwise, that gets a little more complicated because obviously the boundary layer is, changing as you go downstream. We've all done that fluid dynamics problem, right? All right. What happens as you go downstream, the boundary layer? So what happens here is you have to put in a weighted power mean. Okay, you have to put a weighting factor in there by what location you are in the boundary layer. So what location you are from bow to stern. And their weighting factors basically is, your weighting factor is what percentage of the total CF at 15 knots for KS of this, do you have to have as your weighting factor? Okay, again, this is a very clever idea. It took two people who really know a lot about wall-bounded flows and turbulence to come up with this and come up with this kind of simple way of estimating what to do with this. But again, what's our problem? What don't we know? KS. We don't know KS. Okay, so now we have a way to manage if you have heterogeneity. How do we manage that? Okay. All right, so now let's get into how we get KS. This is some tests that we ran at the Naval Academy with Jess Walker, who was with us from the University of Tasmania. She came and built this facility for us and helped us run these experiments. Basically, we have a slime growth facility, okay? This is a tank of water that is basically has this rotating drum in it. And on this rotating drum, we put plates, basically plexiglass acrylic plates that we had painted with ship paint. And we put them in this bath of water that was, had instant ocean with some inoculate, some slime and diatoms inoculate, which we collected from Florida bottom paints. And then we fed them with nitrogen and we gave them sunshine and we heated them, we made them, and we kept them in these plates on this drum rotating for 6 months, 3 and 6 months. Okay, it's a long time to set up for an experiment. Okay, we put this in the depths where no one knew what was going on. So, all right. So why we did it while it was rotating, which was equivalent to 4 to 8 knots, is we wanted the slime that grew while it was under shear, while the ship was underway, because we didn't want to grow it and then put it in the facility and have it all shear off. So we called it tenacious slime. Okay, so these are our tenacious slime experiments. And it was quite tenacious. We had a biologist, Cecily Stepp at the Naval Academy, tell us what we actually had. And we had 3 different plates painted by a very famous paint company. Okay, I'm not allowed to tell you who that is, but they paint a lot of ship bottom paints. Okay, one was a silicone fouling release system, one was a fluoropolymer fouling release system, and the other was a fluoropolymer fouling release system with slime release, A, B, and C. So these are ship paints. We put them in that facility here, which is basically a high Reynolds number channel flow. Ignore this section for now. Just look at this top section. It's an 8:1 aspect ratio channel. Okay, it goes up with a kind of a free stream velocity pretty high. We get up to very high Reynolds numbers. We put smooth walls in the top plate and the bottom plate up to about halfway. And then we put this test section, we put our biofouled plates on the top and the bottom. And the side walls here, they're smooth. They don't contribute much to it. We can account for that. And we had some regions here that we've tested the facility by doing some laser flow diagnostics in here to make sure we have fully developed flow. And then we have pressure traps in the fully developed region. We take replicant runs and we get the wall shear stress within 1%. Okay, and what we did is we ran the facility up to its full capacity before we started taking tests, just to slough off anything that was going to come off up at the highest speeds. Then we went and ran it back down and started our test. And this is kind of what we end up at the end. I'll show you our test results. So after 3 months exposure, this is after we took it out of the facility, not before we put it in. This is what we had. And that's really hard to get how do we characterize that? So we characterized it by percent coverage and what the thickness of this average thickness of this layer is. And we used a paint gauge sensor to get the thickness of that layer. Okay, so specimen A, specimen B, specimen C, and specimen D was basically our acrylic control. That was after 3 months. After 6 months, same things, you're getting a little more. This one has really kind of higher coverage. This one gets a little thicker, kind of a range of tests. And these are the friction curves we got in our facility. Okay, and the error bars on those. Okay, so the black line, this is the friction versus, Reynolds number. And the black line is the smooth line from our facility that we did with smooth plates in there. And specimen C with the special slime release coating does best. And specimen A, and specimen B, and the acrylic control aren't doing very well. They're especially A and the acrylic control. So A, whatever that was not doing any better than almost the acrylic control, causing additional drag. After 6 months, here we have our results again. Again, that slime release coating is doing something. That was compared to, I think, B, so a little better than that. So from this, we can basically get our roughness penalty, and we can get our roughness function as a function of Reynolds number. Okay, and this is actually kind of a disappointing plot to us because it would have been beautiful if all these kind of lined up together, but they don't. Okay, in fact, some of them kind of go off in ways that don't make sense. They don't really scale on roughness height. Okay, so that's a little troubling. So K, the roughness height is not effective by itself in collapsing the roughness function, which is not what you want to see in this type of thing. You have significant variability. However, there were a few that did kind of follow it as we like to see, and a few that got fully rough. And only if they get fully rough can I get the equivalent sand grain roughness height. If they don't get fully rough, I can't do it. And so we came up with a very, very simple kind of, parameter based on the roughness height and the percent coverage to do that. And that only happened for those that had at least a high enough coverage. If those under this 25% coverage, we weren't able to do that. Okay, so, coming up with a parameter for this is proving to be, as we know, very tough. All right, but now we do know it. We did go in and run the tests, so we know this. So we can go to our Granville scaling and we can predict what the penalty will be on a full-scale ship because we ran the test. So there it is. We've got a DDG 51 at 15 knots. The ones for 3 months exposure, specimen A had 6.3% increased shaft power. Specimen C with the slime, the slime release, 1.5% increase. And after 6 months, you can see this is what we had. And I guess the point I want to make is that, this is not completely heavy coatings. This was kind of what you'd call light slime. And light slime, that's predicted but the first slide by Mike Schultz was about 10% increase, okay, which is a significant penalty. Okay, and I'm also impressed this one's doing a pretty good job. All right, so I'm going to take this in a little bit different direction. This is basically, well, I have one more. This was one more test we did. This is obviously before we built the top facility because it's not there. So this is the bottom facility. It's our boundary layer facility. And we've also grew a complete carpet of slime. Okay, and Elizabeth Murphy did this. She came to us as a graduate school intern from the University of Virginia. And we covered the plates, we grew slime, and we took and did laser measurements, laser velocimetry measurements over this to get boundary layer profiles on top of it. And this is just a kind of a snapshot of this, but you can see it causes a big shift in a big roughness penalty. And there's a lot of variability as you go as you go streamwise down the section. And this kind of shows you span-wise what happens, you know, to different parameters. I think it's the stream-wise and the span-wise and the wall number velocity. So you're getting a lot of localized thing going on. But really what's happening with this is you have your roughness, plus you've got these streamers, you know, this kind of grassy stuff. And these streamers flap. And that flapping causes a lot more drag too. And so you kind of can see some flapping stuff going on here in this kind of deficit region. Okay, so these get very, very complicated. All right, and this is what she found as, you know, she's done about to publish this paper where we didn't have 100% coverage, she had various coverage. And just that, you know, it causes a significant roughness penalty. These are very, very large values of KF plus, okay? But they are fully rough. And we'll be able to take these and put them into some of our predictive correlations as well, okay? All right, now we're gonna shift. This is going back to non-biofouling. This is the other world of roughness if you have corrosion on pipes or some sort of pitting on your plate or icing on your wind turbine blades. Okay, how do you predict the roughness? And so I recently published a paper with Daniel Chung and Nick Hutchins and Mike Schultz in the annual review of fluid mechanics, which is basically saying, what is the state of the art of predicting drag on any generic surface? Okay, we can't get biofouling right if we can't get this right too, okay? So I'm gonna show you some classifications. You know, we have to come up with a common terminology. Regular, repeating deterministic scales, right? These kind of look regular. These look very irregular. Two-dimensional, you know, they only vary in one plane versus three-dimensional vary in both planes. Isotropic, meaning it doesn't matter which direction you go from, or anisotropic where, you know, it matters, directional independent or dependent. Monodisperse, polydisperse, one size, multiple sizes, and, you know, and then we get down to broadband spectrum, which is what I've been focusing on recently, multi-scale, okay? All right, and then you have to parameterize it. What are you gonna use? Well, you can use kind of the frontal area, the plan area, the repeating wall unit area, the wetted area, the windward wetted area. You can come up with solidity or density parameters as you go through these. And these work generally well for kind of regular roughness, you know, if you've got something that doesn't have kind of a complicated shape to it. Then if you get into something that looks a little more complex, now we're starting to look like biofouling or such. You get into wanting to take statistics, you know, an average height, some sort of peak to trough height, or some sort of average peak to trough height, an RMS. This skewness and flatness are interesting because the skewness is basically how does your PDF of your height distribution shift? Is it shifted more to the right where everything is kind of peaky? You got, you know, things with tall peaks. Or is it shifted to the left, negative skewness, where things have valleys and pitted? And then your flatness kind of tells you kind of how far your range of scales and how much the kind of the edge scales are contributing to something your flatness does. And then we have something that we measure called the effective slope. You know, are they shallow features or are they really sharp features? And you can imagine in fluid mechanics, well, there's something shallow, you know, and the flow can kind of roll over it, or sharp and you get a lot of separation off it. It's going to really influence the friction drag. All right, so this is an eye chart of the attempts since 1969 to come up with correlations for either the roughness function or KS from all these parameters that I've just listed. And we have a paper in the SciTech conference, and this is also being reviewed for AIAA right now. Just kind of put them all in one place with the same terminology. Okay, I'm just going to go through these. Yeah, there's a whole nother list. They're getting more complicated. And you can see they go from kind of these parameters, which were area parameters and density and parameters, to these more statistical parameters. Here we go. And for sandpaper, sinusoids, pyramids, grip blasted, there's a ship propeller in there. Truncated cones. Truncated cones look a lot like barnacles. Truncated cones is kind of our simulation for barnacles. Again, power loss spectrum of surfaces. Here it keeps going. This is my last slide because we're back to 2021 here. And here we have, you know, black box machine learning. That's where it's headed. Okay, so what we've done is we've gone from roughness being regular to irregular to multi-scale, kind of in our, from 1969 onward. Density, solidity parameters to statistics of the surface elevation map parameters. Number of parameters, you know, less than 3-ish to where we're going to machine learning large. What does it take to do this? This is just an example of the data-driven machine learning approach. I think it's a fascinating way to go through this. What's beautiful about this is look at all these surfaces that this group was able to do. There's a rich information in this. You know, this is a range of surfaces. And the computational simulation skills that have evolved over the past 20 years have made it so they can do this in a very rapid way. They can get the friction results, maybe not all the details of the turbulence, but enough information to get the friction accurately and do this, you know, repeatedly. Okay, so that's amazing. That means this kind of parameter space can really be explored with the simulation capabilities that have come. Okay, and you know, so here's the number of parameter correlations, and you know, there it is. It's pretty complex. All right, so what we're finding from all of these is, from all of these kind of list of parameters and predictive correlation, is there a minimum number of parameters? You need some height, something of a height, an average, an RMS, a peak to trough, some sort of frontal area, which is either a solidity, an effective slope, or a density parameter, and some sort of coverage, which is either the planned solidity, the skewness mathematically relates to the coverage, or a solid volume fraction. Okay, a minimum number. Of course, there could be others for very specific cases. And there they are. This is what, if you want to have a height, there's where your height is. You have a frontal area, you know, this is what we have for frontal area type parameters. And there's our coverage right there. All right, so these are coming out to be kind of the most important parameters. All right, so where does it go back to? I started with one of these slides. We need to develop a robust model that determines the dependence of the roughness hydraulic length scale as a function of the surface topography. That's the goal. We need a low order model. Oops, go back. There's a low order model. Okay, but we need a low order model for KS as well. It needs to incorporate non-homogeneous surface texture, multi-scale Apache, and it needs to be applicable to large scale, high Reynolds number platforms. Where are we and where do we need to go? Well, first off, we don't have enough high quality data sets, even though it looks like there's quite a few. The range of roughness is huge. However, we have the ability now to do systematic variation of roughness scales. We need to cover a wide range of Reynolds number, from hydraulically smooth to fully rough, and we need to explore a very wide parameter space. If we're going to take advantage of this machine learning data-driven approach, let's get a lot of different data, a lot of different situations in there. Okay, these are the things that are going to allow us to do this. We have rapid prototyping to create systematic variation of texture parameters. Okay, I print up surfaces with a very specific statistical distribution. I tell it needs to have a skewness of this, it needs to have an RMS height of this, and it needs to have a length scale of this. Put it into my MATLAB code, send it to the printer, and I can make that tile. And then I can tweak one thing at a time. Beautiful. Okay, before you're just relying on, well, I'm going to get 36 grit, 18 grit, 200 grit, and 400 grit sandpaper. Okay, we've come beyond that. Okay, I've done all those sandpaper tests too. Okay, so this rapid prototyping, you can cover an entire wind tunnel with barnacle type fouling that you've gotten from scans. Okay, computationally, high resolution simulations, direct numerical simulation and large eddy simulations at relevant Reynolds numbers are happening right now. It's amazing where they've come, how far this has come. Machine learning, beautiful, and we're coming up with reduced order simulation models where can we explore the wider parameter space. Do we have to get every detail right? No, but can we get enough of the details right to get the friction right? Okay, lower order models. And we need some full-scale validation. All right, to help the community kind of have this rich database, I developed with a colleague at the University of Southampton, Bharath Ganapratha Subramani, this roughness database. Basically, this is a resource to the community to, drop in your roughness data so other people can make some fun correlations. Basically, we have this database where you can submit your roughness type. It's searchable. You put in your files so people can kind of get what they need to out of this. And the information that's contained is surface information, kind of the XYZ coordinates of your roughness. So you could then put it into a simulation, or you could print it again. Documentation, some sort of folders, anything you need. You can figure out all the surface statistics we're looking for. And it's a resource basically for the community to do this kind of have a one-stop shopping instead of having to sift through lots of papers and such to get this information. So I'm going to stop here and take your questions. But before I do, I have an amazing group at the Naval Academy that's helped me out with this. Not only my colleagues, but we have a hydromechanics lab staff that is phenomenal. We are an undergraduate institution. And I couldn't do all this without basically some lab staff that helped me, okay? We have a technical support shop that helps us make our facilities, keep them running, and helps us do these things. The Office of Naval Research has supported me for many, many years. I know I'm doing relevant research for them, but they've been very generous to me as well. My colleagues have been supported by the Australian Research Council and the Air Force Office of Scientific Research. And this is what I've shown here is work of many, many roughness collaborators. And with that, I'll say thank you and take your questions.
Hey, Karen, it's good to see you.
Thanks, hi.
So you showed this slide where you're trying to summarize all the important parameters and showing machine learning to characterize all this. But what I didn't see was any boundary layer thickness, because the roughness height boundary layer thickness is super important. So if your boundary layer thickness is much higher than the roughness height, then none of this matters, right?
Well, it's assuming that you have some roughness penalty. If your boundary layer thickness is so much bigger than your roughness height, then you're hydraulically smooth and it doesn't matter.
Right, but depending on the ratio, I'd imagine some parameters are more important than others.
Yeah, so I would say they are definitely more important than others. But the important thing that you have to have is similarity between rough and smooth walls. And what breaks down is similarity if the roughness height is too big to the boundary layer thickness. So if K to delta is too big, similarity breaks down and this whole thing breaks down. KS is no longer relevant. Okay, so it's found for turbulent statistics, maybe 15%-ish can break similarity, but mean flow, it's been shown for very, very high for high thicknesses, because what happens is as the roughness gets thicker, the boundary layer gets thicker, right? So it kind of grows with it. Maybe in the kind of the very first part, you know, we're going to kind of have an adapted to the roughness, but roughness gets thicker, boundary layer gets thicker. And similarity has proven to be remarkably and thankfully robust, because without it, the whole thing I've just showed you falls apart. Yeah. Yeah, Andre.
I'm thinking of ways for the Navy to enhance their maintenance schedules. We think about that here in the Army, in the Navy, that our Operating Research Center. Part of what they worry about is, maintenance schedules, time to failure, and anticipating that. One can imagine with all the work that's being done with smart little robots that you could have some robotic sensor-based things that would go around the hull and get some kind of an estimate of biomass accumulation. Probing, sonic probe of some kind. Could that be used to get to the bottom line, which is how frequently you should?
Yeah, actually, it is.
Or when should you trigger? This is going to go to it.
Yeah, they're actually working on that. They're working on having some sort of, ROVs that go around and kind of sense this, which is a very important aspect of it. But when you have that information, you need to know what to do with that information. So they're married together. And the Navy is very, very interested in this for performance savings, but fuel savings, and they're worried about carbon too, right? They're part of our community and what they're doing. And so I think this now really a rich time to come together on this kind of activity to inform them when they do it, and how that the time that they're down in service is worth that, or have more regular schedule. And it also depends on where you're operating, because you're going to get different growth if you're operating in the Mediterranean than if you are in some sort of Arctic region or something. Yeah.
Does the biofilm robotics change, let's say, the response to an acoustic wave as a probe?
I don't know. I don't know. That's not my expertise. Yeah.
Would you comment perhaps on the ISO standard that was put in place a few years ago to help measure the performance of marine bottom paints?
I don't know enough about that to comment on it. You probably do. We went out to the paint companies so we could be using real paint instead of ones that we kind of shoddily applied to our surfaces. We said, if we're going to do this test, we're going to do it to paint that has been applied in a technique that is ship bottom paint. So Mike Schultz is more of an expert on that. I mean, when they've moved away from the copper anti-fouling paints, the problem got worse. And it's always a trade-off, right?
Yeah, and the reason that the ISO standard went into place was to try to reduce the Wild West. Well, my paint's better than your paint, which is better than their paint. We're trying to create some sort of a standard. I'm just curious if you had any reflections on how statistically confident that system is.
Yeah, I haven't studied it enough or know enough about it. Thank you, though. It's an interesting question. Yeah.
So you mentioned that we need to validate all these schedules as the main that keeping some kind of how much
Well, I mean, that would be ideal if you could have your little sensor go down and see what it looks like, and then measure how much fuel you're using. I mean, they know how much power they need to go a certain speed, right? You've got a great performance measure right there. It's integrated. It's integrated over the whole hole. Amazing, right?
So then we can see the scaling.
Yeah, you can see if the scale. Well, the scaling, the Granville scaling is actually quite robust. That does quite a good job. Yeah.
You might want to check in with the Warsaw Voyage group, because we have a very sophisticated system where we measure the performance of the ship every second, if you wish, via satellite, and then because we go to micro weather, we eliminate all those things that are otherwise in the older traditional way. What's North Atlantic?
Yeah.
Exactly.
Yeah.
So you eliminate all those things.
Yeah.
And statistically, you get a fairly strong high level of confidence that this is the performance of the ship. This is what we need to do to improve that performance. whatever.
Absolutely. I think it would be a great data science PhD actually to look at that problem. It would be great. Yeah.
When you're talking about using machine learning for this problem, are you exploring hybrid methods where there is some physics involved as well as some machine learning at the same time, as opposed to like just going over to say a black box machine learning method versus LES simulation or an experiment?
Yeah, I am not the machine learning expert. I'm kind of the experimentalist that provides the data to the machine learning experts, but I know that various groups are doing different techniques right now to look at this. This one I presented was kind of the first paper that was published on machine learning for that. I can't stress enough how valuable it is that the simulation, you know, is able to kind of churn out as many surfaces as they can to go into that database. They're going to put the experimentalists out of business, but that's fine. You still have to do 1 or 2 validation experiments to make sure. Yeah.
Is there a reason when you're drawing the slide why the whole thing isn't submerged?
It was submerged. We just had it up to show you what it looked like. It was submerged. Yeah, and another question I usually get, because I'm going to just answer it because some people always will ask this, is, you know, you grew it this way. Yeah, you're going to follow us out. I know it's coming. You grew it this way and it flows that way. Yeah, we know. We had to do our best to grow it to be tenacious, and we didn't have a long facility, which some have been made that way, but it still hung on there quite well. Yeah. Yeah.
So I teach undergrad facilities in my
Yeah.
class.
Did you tell them KS was not a physical measure of the roughness height?
So
Go back and tell them that if you haven't.
And what I'd like to motivate, you know, it's like, hey, what you're learning in class is relevant, it's in open research and this and that. Do you have, what are some of the numbers in terms of how biofouling contributes to so much, you know, with the amount of extra drag, how much extra CO2 gets emitted or anything like that? Do you have any numbers that
Yeah, I do. I don't have much of my tongue, but if you go to that annual reviews paper, we have a whole section on the economic cost of biofouling and the societal cost of biofouling. So I would look that up, or I can send that to you.
I know?
Okay, great. Yeah.
So you just mentioned that you were an experimentalist, what provides the data, and I would like to ask, how much data do you think is relevant for to train a model, and how much you know on top of that the use for validation?
I don't know how much. I think you definitely need to have, like, I try to provide 5 to 7 data sets, you know, that I can, that have varying parameters to do that. But usually you're going to do one very high level simulation on one of them, and then you're going to kind of have some confidence in that, and then you're going to kind of try to see how far back you can come from that simulation to get the same results, and then move on at that lower order level. Yeah.
Like, how many graphs are which? When you say like data sets, are they like repeated data sets?
Oh yeah. They're on different things. They're on different things. I mean, I try to get the most accurate measurements I can. So, you know, for those friction curves, I did 6 data sets, you know, because I could. You know, could I have done 20 and gotten to half, you know, wall shear stress to 0.5%? Yes, maybe. But we try to get as best we can in the time we have allotted. So we feel like we're giving you, you know, the computationless, you know, as accurate a data as possible. But it's still only as good as everything we have as well. Right? It's really important to do a full uncertainty analysis on what you have and be honest about what your uncertainty is. Oh wait, we got one.
So with the amount of ships that go in dry dock each year.
Yeah.
Is the Navy like placing the ships for you to get the equivalent measurements about ROV or something in the water? So
There's a whole group at Carter Rock who's working with this, and yeah, they're just trying to get more data and working. And there's a big push and a big working group on Carter Rock that's going through this now that we kind of have this kind of skills, and they're trying to couple this idea with what I showed you with the work of how do you kind of average, you know, for different patchiness and different things in the section. So yeah, they're trying to the effort towards it is trying to do it in a systematic way instead of a less ad hoc way that they've done it
Yeah,
before.
you're saying, what paint is gone
Yeah.
versus growth, this is not a perfect surface to start with.
No, it's not a perfect, and every time you clean it, it takes a layer of the paint off, and then you're gonna have to paint it again. I mean, it's expensive to paint, so it's definitely, a trade-off.
For the ships are ground down in the shipyard, it's the blocks. Good.
Yeah, well, a lot of it is you want to, it's different. Yeah, you'd have to do it immediately though, because it's different when it comes out than what's happening when it's underway, which is when the drag happens. So it's really, really tough problem.
Yeah, the control surfaces.
Yeah.
Screw.
Yeah, and the propeller and everything else. Yeah. Yeah.
Occasionally I hear,
Yeah.
somebody believes they have a technology.
Yeah.
Which will give them negative penalty points.
Those drag reducing people.
Exactly.
I know there's a few of them maybe in this room, huh? Yeah, we've tested some of those drag reducing people's surfaces before. Yeah, I think it's possible by trapping air and having other, shear free surfaces. But getting that to be done on real surfaces, on real ships with real biofouling at real Reynolds numbers is a very, very hard problem.
I've always been skeptical of the idea that you're gonna have this nano printed surface that is somehow hydrophobic. You're gonna keep it once.
We couldn't keep it in our boundary layer facility. They sent, there was a Muri on this, and we tested several of those surfaces from different groups, including one at Michigan and one at Princeton. And they worked for a little bit, which is good, proved the theory, but keeping it at Reynolds number in our own facility was hard to do. It's not like it was not well done. It was just that we're not there yet. Yeah. All right. Thank you. Thank you for the good questions and listening. I appreciate it.
Clever ways.
So that was
But also the way they feed it back in. I mean, I'm not their efficiency of their code and how they manage
I wanted to ask